Hey everyone, I get a lot of questions on robot kinematics and how that works, so I wanted to make a new video to go over that topic. If you've ever wondered how a robot arm with 6 separate motors can all work together to make the end effector go perfectly up and down in the Z direction or side to side in the X direction or rotate around a single point in space, that's what the robot kinematics do. That's a lot of math involved in that, and that's what I want to go over here. If you've ever tried to study 6-axis robot kinematics before, or done a Google search on it, you usually end up looking at something like this that has some diagrams, some tables, gets into formulas, and before you know it, you're looking at transformation matrices, and you just end up more confused than when you started. These are all usually written from the perspective of somebody who already understands it, so I want to try and make a video that explains it, for the rest of us, that goes to a beginner level. So I'm a visual learner. I need to see the math. I need to see the problem worked out in front of me. So what I've done is I've put together this Excel spreadsheet where I have all the robot kinematics all worked out in front of me, and I can change the values and see everything change and see how the formulas all work their way through. You can get this spreadsheet here on the AR4 project website here at annandrobotics.com. If you come to downloads and then come down here to documents, we have the kinematic calculation sheet. On this sheet, on the left side, I've got the forward kinematics worked out, and on the right side, I've got the inverse kinematics worked out. So before we get into any of that, we need to understand what is forward kinematics and what is inverse kinematics. So to illustrate the difference between forward and inverse kinematics, I have the AR4 control software open here, and then I have a camera set up on the robot so you can see it move. The forward kinematics are when I know what the joint angles are, but I don't know what the Cartesian coordinates are for the XYZ yaw, pitch, and roll position of where the end effector is out in space. So as you can see here, when I jog the robot using joint mode, changing the joint angles, the forward kinematics calculates out and tells me what the XYZ yaw, pitch, and roll position of the robot is. You can see every time I jog it, the Cartesian coordinates update there. Now, the inverse kinematics is the opposite. That is when I know what the Cartesian coordinates are, but I don't know what the joint angles need to be to make that happen. So when I jog in the Z direction, for example, if we jog straight up, the inverse kinematic calculation is what figures out what the joint angles need to be to make that move happen. So every time I jog in Cartesian, you can see the joint angles updating. So that is the inverse kinematic calculation that makes that happen. So now that we know the difference between forward and inverse kinematics, I'm back on the spreadsheet here just to show you a few things and how the spreadsheet works. On the left side is the forward kinematics like we talked about before, and up here in these cells here in green, this is where I can input the joint angles, and this will output the Cartesian coordinates. So when I know the joint angle, for example on joint 2, if I change that to 20 degrees and enter that, it calculates through all of these transformation matrices and then spits out what the Cartesian coordinates should be. Now, on the inverse kinematic side, it's the same thing. You can input in what you know the Cartesian coordinates need to be. It will run through all these calculations and spit out what the joint angles need to be. So to illustrate this, for example, I could take and copy the values from those fields and then paste in the values, and you can see it updates, and now it spits out what the joint angles should be. So you can see that right here J2 just updated to tell me that to achieve these Cartesian coordinates, that joint 2 should be changed to 20, which is what we put in over here. So now we're going to really get into the forward kinematics and how the forward kinematics works, and we'll do the inverse kinematics later towards the second half of this video. So on this side, on the forward kinematic calculations, you can see there's a lot of formulas here. There's a table of parameters, and there's a bunch of transformation matrices here. So before we get into all that, let's talk about what actually we need to do to calculate the forward kinematics. So to calculate the forward kinematics, to be able to take each known joint angle and calculate out where the end effector is in space, we need to define or know what the difference is throughout each joint. I need to know the difference from where the base is to where joint 1 is. not only the difference in rotation, but the difference in the distance. And then I need to know the change in distance and rotation from joint 1 to joint 2. And then I need to know the change in rotation and distance from joint 2 to joint 3, and so on. So what we need is some type of a mathematical representation of the change from the base to joint 1, the change from joint 1 to joint 2, and so on throughout the entire robot, so that we have a definition of the translation from one joint to the next throughout the robot. And what that is a transformation matrix. So what this matrix is a definition that defines the rotation and position of the base. And then the next one, for joint 1, this matrix will define the difference in position and rotation from the base to joint 1. Then this matrix will define the change in position and rotation from joint 1 to joint 2, and so on. So each one of these matrices is defining the change from one joint to the next. So then once we have all of these matrices built, we can multiply this matrix times this matrix times this one times this one, and go through the entire kinematic chain, so that once we're done multiplying all these out, this last one will give us some information that we can extrapolate the Cartesian coordinates of this position in space. Now this sounds pretty daunting and complex, so we're going to have to take about 3 steps back and go back and talk about some basics of rotation and translation. So when I reference a transformation matrix, or what's known as a homogeneous transformation matrix, this is a 4x4 matrix. This is a block of 4 rows and 4 columns where we can place in all of our numbers. And this is a notation or a form factor for linear algebra that lets us do linear calculations on these numbers. So this 4x4 matrix encompasses numbers that represent rotation and translation. That is, you know, the yaw, pitch, and roll plus the displacement and the x, y, and z. So these first 3 columns and rows in the matrix, these first 3 are what handles the rotation, and this is what's known as a rotation matrix. So that's what I want to start with, is let's just talk about a rotation matrix, and we'll get back to the rest of these fields and how they work. But for right now, we're just going to talk about rotation. Now, you know, when you think of rotation, you're probably used to Euler angles, you know, where you're used to the yaw, pitch, and roll. And so this rotation matrix is, in linear algebra, a rotation matrix is just a transform matrix that allows us to perform rotation in 3D space. So this format, this you know, linear algebra or matrix format, that can be a little bit confusing. So linear algebra is a big topic. There's a lot of websites that go over linear algebra, on betterexplained.com. There's an intuitive guide to linear algebra, and this kind of goes over how, you know, algebra means relationships, and linear algebra means line-like relationships, and it goes through and explains pretty well linear algebra, and I'll put a link to this website in the description. But this just goes through some examples and goes through and gives you some equations and explains how these linear calculations are done, and then how those linear calculations can be put into a different notation, into a matrix notation, and then how different operations can be done across these you know, matrices. So this is a good article. There's also you know, on Khan Academy, there's a lot of good videos. There's one on Vector Intro for Linear Algebra that kind of explains how a vector can transform into the linear algebra into a matrix notation. So there's some good info out there to help you grasp the concept of linear algebra. So now let's talk about what it takes to convert angles to a rotation matrix. Right here I have pasted into the Excel spreadsheet, I've pasted in the formulas for converting angles to rotation matrices, and you can find this on Wikipedia under the rotation matrix page that they have. So it goes through a lot of examples, and you can find that information down here on general 3D rotations. So this section here is on the yaw. This is the formula for converting the Z rotation to a rotation matrix. This one here is for the pitch. This one is for converting the Y rotation to a matrix, and this one is for the X rotation to a matrix. So in this example here, I've got set up. In this example, we're gonna do 3 degrees for the Z, 10 degrees in the Y, and 5 degrees in the X. So before we can do this, we need to convert these to radians. And so you might ask, well, what are radians and why do we use radians instead of degrees? Degrees are something that was more of a cultural, I'm not sure what the history is on how we came up with 360 degrees on a circle. There's a few different theories on that, but it's not a very mathematically sound way to define an angle. So we're going to use radians. What a radian is when the arc length is equal to the radius. That creates a unit vector. So for example, my radius, when it's equal to the arc length, that angle is 1 radian. And so radians provide a suitable unit for measuring angles in circular motion and allow for the definition of sine and cosine as functions for all real numbers. So you can see here where we have a single unit vector, you can put a triangle in here, and the vertical height and horizontal width change with the angle so that the trigonomic functions of sine and cosine can measure its height and width. So this allows us to, using radians allows us to use sine and cosine in our math. So radians are just a more sound way to deal with angles when it comes to math. If you want some more information on radians, Khan Academy has a great video called Intro to Radians. I'll put a link to this in the description. This is a great video, so if you have any questions on that, I would highly suggest pausing now and going and watch this video. This is a great example to explain it. So going back to our example, the first thing I want to do is convert 3 degrees to radians. So I'm just going to say that this equals radians of this cell. And so that's what the radians of 3 is, and then we can just pattern that down. And so now we have the radians available to us for each of those angles in degrees. The next thing we're going to want to do is take and pattern this formula over to our to where we're going to work this out. You'll notice that we have cosine, sine in these first 4 cells, and then these are zeros and ones. So we want to just pattern or copy that over. So I'm just going to put a 0, 1, 0, and a 0. And so in this first cell here, I'm going to take the cosine of our Z angle, which is this. So we're just going to just say equals cosine of 3 degrees radians. And so that's our value for this one. This one, we're going to say that this one equals negative sine of 3 degrees radians. For this cell, we're going to say that this one is equal to sine of 3 degrees radians. And this cell is equal to cosine of 3 degrees radians. So now we have a rotation matrix, and this rotation matrix represents in matrix form the rotation in Z of 3 degrees. So now I'll go ahead and do the same thing in these matrices. I'll do the same thing for the Y rotation, and then the same thing for the X rotation. Okay, so now I've finished filling in these last 2 matrices for the Y and the X, basically following the same thing we did on the first one. I just copied in the zeros and ones into each of these, and then applied the cosine and sine as shown here to these cells here. So now I have 3 rotation matrices, this one for the Z angle of 3 degrees, this one for the Y of 10 degrees and this one for the x of 5 degrees. So now if we want to start working on creating a rotation matrix that encompasses all 3 rotations into one matrix that contains a complete rotation of 3, 10, and 5, of that complete rotation in one matrix, we can start with matrix multiplication. And what we're going to do is we're going to multiply the Z matrix by the Y matrix, and that will give us, so I'm going to put that right here in these cells here, and what that will give us is a matrix that represents the rotation of the Z and the Y, and then we'll take this matrix and multiply it by the last one, by the X, and then we'll put that here, and that will give us a matrix that encompasses or shows the complete rotation of all 3 angles right there. So matrix multiplication is fairly simple. It's just the first row times the first column for the first value, and then the second one will be the first row times the second column, and then the third one will be the first row times the third column, and it will work that all the way through. So I'll show you how we do that. So right now we're going to say that this cell equals the first row times the first column, and then that's going to be then we're going to do a plus, so we're going to add that to the first row times the second column, and then plus the third row times the third column, and we'll hit enter. And so that's our first value. The second value is going to be equal to the first row times the second column plus the second row times second column plus third row times third column. So that's that value for this one. That's going to be equal to the first row times third column plus first row times third column plus third row times third column. And so that's our value there. For the next one, that's going to be equal to, and that's going to be the second row times first column plus second row times second column plus third row times third column. This one is going to be equal to second row times the second column plus second row times second column plus third row times third column. This one is going to be equal to, equal to second row times third column plus second row times second column plus okay, so I finished filling in this bottom row here. So you can see if we click on each of these, you can see top row, first column, top row, second column. Click on that, you can see it highlights top row, third column. Then we can look at the bottom one that I finished. Bottom row, first column, bottom row, second column, and bottom row, third column. So that is how you do matrix multiplication manually. Excel has a formula for doing it automatically, and just like any other programming language, Python or whatever, is going to have a math library that'll do it for you. But I wanted to show you how it's done so that you understand it. So I can highlight a 3x3 space of 9 cells, and I can put in equals and then MMULT for matrix multiplication, and then I want to duplicate what we did here just to verify that we did it correctly. So I will highlight the Z matrix, and we'll put in a comma, and then highlight the Y matrix, and end the brackets. And then in Excel, for the matrix multiplication, for it to populate all 9 cells, you have to hit Control, Shift, and Enter, and so that'll populate all 9 cells. So now we can look at it and we can see that it agrees with, that it verifies that, I punched everything in manually correctly. So I just wanted to show you that. So from here on out, we'll just use the matrix multiplication formula. So I'm going to delete that there. And so now the next thing we need to do, so this matrix here is Z times Y, and now we want to get a matrix that has the complete rotation of all 3 axes. So this one we're going to do equals matrix multiplication, and then we're going to multiply the one we just did, which is the Z times Y, and then we'll put comma, and then we will highlight the X matrix. So this should give us a matrix that encompasses all 3 rotations into one matrix. So this puts Z, Y, and X all into one rotation matrix there. So now, just to illustrate and show you, and just to prove out, that this has the correct rotation, this formula here is how you extract Euler angles from a rotation matrix. So let's start out with the Z rotation. So we'll come here, and for this output, we'll put in right here, this is going to be equal, and we'll do A tan 2. Now, A tan 2 is supposed to be in the order of the Y and then the X. For some reason, Microsoft and Excel does it backwards, and it confuses a lot of people. I'm not sure why they do that, but so we have to put these in backwards. So right here in A tan 2, you see rotation cell 2-1 and rotation cell 1-1. So this little map up here corresponds to our rotation matrix here. So R11 is the top left corner, and R33 is the bottom right corner, and so on. So so this is saying R21 and R11. We need to go backwards, so we're going to do R11 first. So we'll put in this one, and then we'll do a comma, and then we will do 2-1 next, and we'll close the brackets. And so you can see that this is outputting 0.05236, which is what we have out here. So that agrees that it is extracting the Z value from this rotation matrix. And then, so we've got the formula for Y. I already wrote this out earlier, so you don't have to sit here and watch me struggle through it. So we will put that formula in there, and you can see that formula is A tan 2, and again, it's backwards. So you can see here it's negative R31, so the negative R31 is on this side, and then the square root of these 2 cells to the second power is over here on this side of the formula. So that's that one, and then the last one, the X formula. Oops. Enter that, and so you can see that gives us 0.8727. So then in this cell, I'm going to do equals degrees, if I can type, and then we'll select that cell, close the brackets, and then we'll pattern this down. Whoops, let's try that again. Pattern that down. So now you can see that this is extracting the values from this rotation matrix, and so you can kind of see it work all the way through, how we've applied, we've changed from the degrees to radians, applied the radians using these formulas to each rotation matrices, multiplied them all the way through to a matrix that contains all of the rotations, and then how we've extracted those back out and converted them back to Euler angles. So if I come up here and I change this to 12 degrees, you can see down here it proves out the formula there, that it's working all the way through it. Okay, so now that we've kind of gone through the exercise and shown you how to do matrix multiplication and how to multiply rotation matrices by one another, the next thing that I want to do is show you is that I showed you the hard way here. We did each one individually. We did the z, the y, and the x separately, multiplied them all together to get one rotation matrix. But what I want to show you here is that right here, this formula, this template here, this is basically how you do it in one step. This takes this one, and this one, and smashes them all together into one formula so that you can do it without having to rotate, multiply, doing each one of them separately and multiplying them together. I just wanted to show you the hard way before I showed you the easy way so that you could better understand. So what we can do here is create a, we'll just create another, we'll enter in another matrix right here, another rotation matrix, and I will put in all these values the same way we did earlier. So I'll pause it right now, put all those in, and then I'll show you what that looks like. Okay, so I filled in this matrix using this formula up here. So if I click into the cell, you can see it's cosine of z times cosine of y, just like it shows here. And if we click on the second one, you can see it's cosine of z, sine of y, sine of x, and that's of course of the radians, minus the sine of z times the cosine of y. So that's this formula right there, and then this one is this formula up here, and so on. So I filled this all out, and so you can see that both of these matrices match. So what I want to illustrate here is that you can build a rotation matrix with all three rotations in one step rather than doing it the long way, the way I showed you here. But I just wanted to show you, the way it can be done and how to multiply rotation matrices through each other to get the answer. And then I'll show you the easy way last. And then, so we'll delete that. And the other thing I wanted to point out that's an important note for something a little bit later on is that if you notice up here we've got the zeros and ones, so I just want to copy these in here. 0, 0, 0, 1, and then if I copy in the 0, 0, 1, and then over here put in the 1. So what you can see here is what this is this is a zero rotation matrix. So I guess what I wanted to point out here is that when you have in a diagonal from the top left cell through all the way through, when those are all ones and everything else is zero, that is zero rotation. So that's just an important note. That's going to be important later. I just wanted to point that out, that that's a zero rotation matrix. Okay, and then one other thing I wanted to point out, just to make sure in case it isn't clear, you can multiply a rotation of zy and x by another rotation of zy and x. So in this example, I realized we only multiplied, a rotation of z by y by x to get the total, but you can also multiply any rotation of all three by any rotation of all three. So for example, here on the robot, when we get to this, when we multiply these through each other, this is going to be a rotation of what the x, y, and z rotations are times this one times this one. So you can keep multiplying one rotation through another. So I just want to make sure that was clear, that you can multiply a rotation of all three by another rotation of all three. So now let's talk about, we've talked about rotation, now let's talk about translation, because now we want to, when we rotate, when we multiply these values through each other, we want to know what the change in rotation is from each one, but we also want to know the change in position as well. So what that is that's going to be a homogeneous transformation matrix, not just a rotation matrix. So a transformation matrix, instead of being a 3 by 3, it is a 4 by 4 matrix. So we're going to take this rotation matrix that we had and add and turn it in from a 3 by 3 and turn it into a 4 by 4, so that this top left section handles rotation And over here, this is what's going to handle translation. So this is going to be displacement in the X, this one is displacement in the Y, and this one is displacement in the Z. So, for example, let's say in our robot that we're working on the change from axis 1 to axis 2. Let's say that's 100 millimeters up in the Z and 50 millimeters over in the X, forward in the X, for example. So what that would look like is that would be 50 millimeters in the X, 0 millimeters in the Y, and 100 millimeters in the Z. So that's what that would look like if we were trying to build a matrix, a transformation matrix that contains some rotation and some translation of position. Now, a matrix, we want it to have, we want it to be a square. We want it to be 4 by 4. We don't want it to be 4 by 3. For matrix multiplication, they need to be the same. Your matrices need to be the same row heights. So what do we put in these? Because these are basically unused cells. Well, if you remember earlier, our zero rotation matrix for a 4-cell, for a transformation matrix, zero rotation, zero translation is going to be the same thing. It's going to be 1s across the corners, and then it would be 0s everywhere else. So this right here is a zero rotation, zero translation transformation matrix. So what we're going to do is this last row here, we're going to put that here. So since these cells basically aren't used, that we're going to have 0, 0, 0, 1. So that's how we finish filling in the 4 by 4 matrix. So now we can complete the grid, and we've got a full 4 by 4 matrix. And now this matrix, contains, the rotation, the change in position, and then the other cells are filled in. So now we have a complete transformation matrix. So now we go back to our Excel sheet that we started out with, and this might start to make a little more sense here, because now you can see we've got some of these transformation matrices where this is the this one shows the change in rotation and position from the base to joint 1. This one is the change to joint 2 and to joint 3, 4, 5, 6, and so on. And then if we look at this one, R02, that is the rotation from the base to from joint 1 to joint 2, and then this one multiplies just like we did before in the earlier example. This takes the result of that, multiplies it times joint 3. This one takes the result of that, multiplies it times joint 4, and so on. So we start building out and multiplying through to figure out what our final x, y, and z and rotation of the end effector is going to be. So there's a little more to it. We'll come back to this, but I just wanted to see if that, point out that this is going to start to make a little more sense now that we're getting through what the transformation matrix looks like right here. So now let's talk about what it's actually going to take to create a transformation matrix for the robot. So we will need to create one for every single joint. So let's do an example of creating the transformation from joint 1 to joint 2 to create that transformation matrix. So I've got my robot here. Let's say that this is my frame for joint 1 and this is my frame for joint 2. The z-axis is kind of hidden inside here for joint 1. So let's say that's our z-axis, and our y-axis goes along there, and the x-axis is pointing straight out. So in order to make the translation from this frame to this frame, I would have to rotate this frame 90 degrees about the x-axis to make these two match. So I've got a 90-degree rotation there. So I would have to create a rotation matrix and put in all the values for a 90-degree rotation in the x-axis. And then, let's say, for example, our joint variable, let's say our robot moved, let's say 20 degrees on joint 1, then I would need to also create a rotation that indicated a rotation of 20 degrees in the z-axis. So I'd have to multiply those together, and then I would have an overall rotation of 20 in the z, 90 in the x. So let's say this is our rotation matrix that has this information within it, and then we would also make this a transformation matrix, adding the other cells that we need. So let's say from our earlier example that the translation from joint 1 to joint 2, let's say that's 50 millimeters in the x, 0 in the y, 100 in the z, and then we'd add a 1, a 0, a 0, and a 0. And so that's how we would create a transformation matrix going from this frame to this frame. So we would have to do that throughout the entire arm. There's a bit of math in there. There's it takes quite a few steps. It takes 6 parameters to do that, to make that transformation. So most people don't do it like this. They use a shortcut called the Denavit Hartenberg parameters, and so that's what we're going to talk about next. So the Denavit Hartenberg parameters, or DH parameters, these were created back in 1955 by Denavit and Hartenberg. And what these are is a shortcut or a formula to be able to create each of these transformation matrices a little bit easier, and using only 4 parameters instead of 6. So the DH parameters are also used in conjunction with the DH table. So we've got a table here of 4 parameters per joint. So before we get into that, there are 4 rules that you have to follow for the DH parameters to work. And so these rules are: number 1, the z-axis has to be the axis of rotation. So if we look at our robot here, we can see, I'm going to use joints 1, 2, and 3 as examples here. So in joint 1, the z-axis, the blue axis here, that is the axis of rotation. On joint 2, the blue line there, that's the axis of rotation on joint 2. And the same thing on joint 3, the z-axis is the axis of rotation there on that joint. So the second rule is that the x-axis must be perpendicular to the z-axis in the frame that we are coming from and the frame that we're working in. So looking back at our model here, so the x-axis has to be perpendicular to the axis we're coming from and going to. So using joint 1 for an example, the x-axis has to be perpendicular to both the z-axis for this joint and for this joint. So you can see that by the x-axis coming out in this direction, that satisfies that rule, that it's perpendicular. And then you can see here on the next joint, joint 3, that the x-axis, by having it point straight up, it is perpendicular to both of the z-axis from both the joint that we're working in and the previous. The third rule is that the y-axis must follow the right-hand rule. So if you're not familiar with the right-hand rule, if you hold your hand in this orientation shown here, your thumb is the z-axis and the x is your index finger, then the y-axis has to be coming out in this direction to the left, as shown here by your middle finger. So we can see here on the model, if the blue arrow going up is my thumb and the red arrow is my index finger, that would make my middle finger coming out to this direction, the direction that the y-axis needs to be. The same thing here, if this axis coming straight out was my thumb and this was my index finger coming straight out, then that puts the y-axis coming straight down. And then in this case here, if this was my thumb in this direction and this was my index finger pointing out, that puts the y-axis in this direction. And the fourth rule is that the x-axis must intersect the z-axis from the previous joint. So if we look at the x-axis for joint 1, if we just do an imaginary line that goes to infinity in both directions, and then we look at the z-axis for the previous joint, and it goes in infinity in both directions, they do intersect right here. So they're on the same plane. basically. So the only time this really causes a problem if you have an offset joint, if joint 1 was offset to one side, you would have to create your frame for your robot and define it with the frame offset so that these intersected to keep that true to satisfy the fourth rule of the DH parameters. So as long as we follow those 4 rules, we can set up our robot or configure our robot in a couple of different ways. I mean, not only is a robot, robots going to be different from one another as far as their size and their the length of the arms, but you can also change the way that the joints are oriented to each other, at least as far as where 0 degrees is at, and some of the configurations. So, for example, if we open up a ABB robot, we can see that with all the joints at 0 degrees, the robot is in an L configuration. But if we open up, let's say, a KUKA robot, you can see that with all the joints at 0 degrees, the robot is laid out flat like this instead of an L configuration. So, KUKA has made their robot a little bit different as far as where 0 degrees is at. By the time you're done doing all the math, going through all the transformation matrices, you're still going to end up with the correct value at the end of where the end effector is. They just have a little bit different configuration. Then, for example, if we go back to the ABB robot, if we jog joint 3 in the positive direction, that brings the arm down. Now, if we let's look at a FANUC robot, and we jog J3 in the forward direction, that brings it up. So they've defined their frame a little bit differently. So that's kind of an example of how you can still follow the parameters, but you can set up each robot a little bit different. So you will see tables that are set up differently. So let's look at the table for the AR4. This first column, this is theta. So this is defined as the angle about previous Z from the old X to the new X. So basically what this is this is your joint angle. This theta, this is your variable. So when you jog your robot, if you jog joint 1, this is the value that's going to be being changed before you run the calculation on where the Cartesian coordinate is for that joint position. And you can see here that J2 is J2 minus 90 degrees and J3 is J3 plus 180. So that's just, these make it so that with all the joints at 0, the robot's in the L configuration, the same as the ABB robot we saw earlier. The KUKA will have a different value. It won't be minus 90 and plus 180 here. There'll be different values that are added to or subtracted from the joint values for that particular configuration. But that's what the theta column is. That's the joint angle basically. The alpha column, that is the angle about common normal from the old Z to the new Z. So if you remember in that previous example where we had to rotate the frame 90 degrees, that's what this is. This is how the joints, the main frames are rotated from one another, from the old Z to the new Z, and that's going to be about the x-axis. So in this case, from the base frame to joint 1, it's a negative 90 degree rotation, 0, a plus 90, a minus 90, a plus 90. So different robot configurations, depending on how they've set up the robot, these numbers could change some. Now the D variable, this is the offset along the previous Z to the common normal. So this is going to be one of our arm lengths. And if we look at this little skeleton of a robot here, you can see that D1, for example, is the offset along the Z-axis for joint 1. So on the AR4 robot, that's 169.8. And then D4, that's this one, along the upper arm. Its length on D4 is 222.6 millimeters. And then D6, from the end of the end effector over to the wrist, that is 36.3 millimeters. So this is just going to be dependent on the physical, characteristics of your robot. And then A, the length of the common normal, that is basically going to be the length shown here, the X offset, the common normal offset. So you can see A1, that's a shoulder offset, so that is 64.2. And then we've got, for joint 2, we've got the A2 value. So that's right here, that's this offset in that direction, and that is that arm length is 305 millimeters long. So now we've gone through how to build kind of the blueprint for your robot, or the the DH table for your robot. Once you have that, you can then start applying these values to this formula, and then build this out and create your transformation matrices. So for example, we have cosine of theta, so that would be, we would put the J1 value here, we'd put the J1 value here, and then we have cosine of alpha, so this value here, we would put that here, and then we have, in this one, we have the sine of theta, so we would put our joint angle here, and then we would put the minus 90 here, and we would keep doing that through all of these. So these, all of these in our rotation area of our transformation matrix are going to use the angles, the theta and alpha values. And then over here, this portion, as we know in the transformation matrix, that handles our transformation in position. So we have our link length D of 169.8, and so that value is going to be placed here, and then we have our link length, arm length A, and that's going to be placed here and here, and then we have, that's multiplied by cosine of the joint angle theta. So what basically, once we've taken those 4 parameters, and I didn't circle the A value that we put here and here, so once we've applied all 4 of those to each one of these values in here, we can plug those in and basically create, and put all that right in here, and that basically creates our transformation matrix. So basically that's what all there is to it, is just plugging these values into it and creating each of the 6 matrices for each of the 6 joints. Okay, so now that we've gone over how to create transformation matrices using the DH parameters, let's go back to our spreadsheet, and we're going to go through the entire for kinematic side. This entire side should now make sense to us. We've got our input up here. This is where we input what our joint degrees, what we want them to be. This column right here just takes that and transforms it to radians. So this whole column is just the radians of the cell next to it. And then in our DH parameter table, we've got our theta, or our joint value for joint 1, and that is just grabbing directly the radians. The second one for joint 2 is grabbing this value minus radians of 90, and if you recall earlier, we talked about that's how we defined our frame setup for our table setup for joint 2. And then joint 3 is going to be the joint 3 value plus radians of 180 degrees. It's just what we had here, and so on. So each of these just grabs the radian values. Then for our alpha, this one is radians of minus 90, 0, plus 90, minus 90, plus 90, and 0, which is what we had here for how we defined our robot frames. And then the D value and the A value are link lengths. Those are the same as what we talked about earlier here. So this is our DH table that we've built. And now here we have our transformation matrices for joint 1. And if we look at our formula, which I've got right here, it just follows this formula all the way through. And this is the same formula we looked at on this sheet right here. It's the exact same formula. So for example, right here, this first value is cosine of theta, same as we see there. This one is negative sine of theta times cosine of alpha, which is the same thing we have here. And so every one of these is just an exact copy of this formula here, and these are all just grabbing the values from this first row for joint 1. This one down here, joint 2, it's the same thing. It just grabs the values for joint 2, joint 3, joint 4, grabbing the values from the 4th line, and so on. So every one of these, 1, 2, 3, 4, 5, and 6 are exactly the same, following that formula. Now what I haven't talked about yet is the tool frame. So what I've created here is a tool frame. If you recall from the first seen in the video, the robot was articulating about this this pointer. So the tool frame is so that you can define how long your tool is, so that you can do things like this. Tool frames are used in all kinds of applications. It's used for weld guns to define where the tip of the welder is, glue applications where the end of the glue gun is, and it can be anywhere you want it in X, Y, and Z, pitch and roll based off of the frame of the end effector. In this case, this one was 120 millimeters straight out in the Z direction, and so that's all I did was define my tool frame to be 120 millimeters. So if we go back here, this tool frame here, I basically created this in a manual way, the way that we did in this example, the way that we created this rotation matrix, and then we turned it into a homogeneous transformation matrix. That's all I did here. So these rotation cells, if we look at the first one, it's the exact same formula as right here, and it basically follows that template right there. So that's what these are, is following that template. And the inputs for these I put up here. This is my input for my tool frame. So these are the input values that it's looking at to create this. And then, for example, the Z value is looking at the Z value here. The Y value is looking at the Y input. So this transformation matrix is just manually created from this input right here. And so, for example, the tool that we showed you right here, if I wanted to apply that, I would just come in here to the Z, put in 120 millimeters, and then if we come down here and look at our tool frame, we've got 120 millimeters. So basically what this does is this tool frame just stacks on one more transformation onto the end of our robot to tell us where the very tip of that tool pointer is. So we've got all 6 joints, and then we've stacked on an extra transformation matrix to tell us where the tip of our tool is going to end up. So now I have 7 transformation matrices, and now all we do is just multiply those through each other. So this first one for R02 is joint 1 times 2. The transformation matrix for R03 is R02 times joint 3, and then this one is our product of that is the R03 times joint 4. The R05 is 04 times joint 5. So you can see all we're doing is we're just multiplying the product of the previous multiplications times the next joint. R06 is R05 times joint 6, and then R0T, our last one, is R06 times our tool frame. So now this frame, this is our final output, this is our last frame that tells us what we want to know. And so if we come up here and look at our output of where we're publishing the output of what the XYZ yaw, pitch, and roll is of the robot, if we look at the X position of 281.416, you can see that it is simply grabbing that from the X value of this frame. The Y of the output is grabbing from the Y cell from that final frame, and the Z value is grabbing from the Z value of that frame. And then we have this formula here for extracting the yaw, pitch, and roll in degrees from that frame, and that's what this ATAN2, and then it goes through and grabs ATAN2 of those 2 cells. The rotation in Y, that grabs the ATAN2, and then this formula, same one right here, grabs it from those 3 cells from the rotation portion of that matrix. And then the ATAN2, this formula here, grabs those 2 cells from this portion of the rotation matrix and presents the radian values, and then this is just degrees of those, so that tells us the final degrees of the where the robot is at. So so that completes the forward kinematics and how the forward kinematics on the robot works. So just a quick recap here. We've got our DH table that defines basically what our robot looks like. Those values are ran through this formula to create each of these frames for each joint. all the way down through the tool frame. We multiply this one times this one to get this. We multiply this one times this one to get this one times this one to get this, and so on all the way down until we have a final transformation matrix, and then we extract the XYZ and then use those formulas to extract the yaw, pitch, and roll from the rotation portion of that matrix to spit out what the final values are there. And then again, just to recap what the Ford kinematics do, when I set these joint values, this is how the software figures out the XYZ yaw, pitch, and roll positions of the robot. So in the next half of this video, we're going to go over the inverse kinematics or reverse kinematics. That is where we know what we want the X, Y, and Z to be, but we need to figure out what the joint values are, so we'll do that next. So now let's talk about the inverse kinematics or the reverse kinematics of the robot. On the spreadsheet, this is on the right-hand side where we've got the green bar across the top. This is where we've done all of the inverse kinematic calculations on the sheet. These cells right here, this is where we input what we want our Cartesian coordinates to be. It'll run through all the calculations and then spit out what the joint angles need to be to achieve that. So this is our input on the sheet, and this is our output on this side of the sheet. Now, there are a couple different ways to do inverse kinematics. There's a geometric method and an algebraic method. We're using the geometric method. I think that's the simplest and easiest to understand. Keep in mind that this model, this calculation, is the simplest form of geometric calculations, and this is based on the this robot's configuration. This is the with all joints at 0 with a robot in an L configuration, so that's what this is written for. So the kinematics can get a lot more complex when you're putting in conditions for different robot configurations and things of that nature. So before we get into getting into the calculations on the inverse kinematics, I wanted to kind of explain a concept on the geometric calculations. So, picking a point out in space and then from that point trying to figure out, what each of these joint angles needs to be to make that happen is a pretty tough job. So the concept here that I want to convey is that mathematically what we're going to do is we're going to take the robot wrist and we're going to detach it from the robot. So in doing so, if you think about this, on the wrist, we have 3 axes. We have axis 4, which spins along that axis. We have axis 5, which spins along this axis. And then we have axis 6, which spins along that axis. So if you look at it from that perspective, all 3 of these joints intersect in one spot here in the center. And what that is known as is the spherical wrist. That's the robot's spherical wrist. That's the center of J4, J5, and J6. And if you think about it, these 3 joints provide all the orientation for the end effector and how the end effector is oriented. So these 3 joints provide all of our orientation, and then these 3 joints provide all of our position. So if we were, for example, to imagine that I hadn't removed the wrist, but let's say our spherical wrist is right out here somewhere. And then we look at the configuration of this arm, from the spherical wrist back to joint 3, from joint 3 back to joint 2, and then from joint 2 back to, the offset here back to joint 1. More or less what we end up with is a triangle. And these 3 joints primarily dictate position in the world. So joints 1, 2, and 3 are going to dictate position, and joints 4, 5, and 6 are going to dictate orientation. And what this allows us to do is quite easily, from our Cartesian point in space, once we figure out where that spherical wrist is, we can run some trigonometry against these lines here and figure out pretty easily what joints 1, 2, and 3 are, and then from there we can work backwards to figure out what the orientation is of the wrist. So let's say we want to start out with joint 1. We want to figure out what the joint 1 angle is. So we're looking at a top-down view from the robot, and let's say that we've got joint 2 leaning forward a little bit, maybe around 20 degrees, and then let's say that we want to move joint 1, say 30 degrees approximately there, and we want to figure out what that angle is from the geometry. Well, if we're doing that, we're going to look at this axis from, from joint 1 over to where our robot is. We want to figure out what that angle is of joint 1. So if we were going from this point, from our end effector to right here, that's what we want to, that's the angle we want to find. But what I want to illustrate here is then if I, for example, if I jog joint 5 down and move joint 4 over, well, now my end effector is over here, and I'd actually be getting the wrong angle. That's not really truly the angle of joint 1. That's going to be an angle of joint 1 plus the offset of how our wrist is oriented. So that's the point I wanted to make as far as one of the reasons we need to figure out where the center of the spherical wrist is before we do any of these calculations, so that when we do these calculations, we're going to get the angle from the spherical wrist over to our 0 line and get the correct angle. So what we're going to need to do is figure out where this spherical wrist is. So we're going to have the XYZ yaw, pitch, and roll for where the end effector is. So let's just pretend right now, let's say that we've got a tool attached to our robot. Let's say we've got a pointer or a weld gun or something like that. And so the kinematics, the XYZ yaw, pitch, and roll of the robot is going to be right here. And so we need to work our way backwards up to the spherical wrist to figure out what the XYZ yaw, pitch, and roll of that is. So we know what that is. We're going to work our way back to this point right now. So that's our first step. So we're going to work our way back from the end of the tool to the end effector and what that point is, and then we're going to work our way back from the end effector back to what the center of the spherical wrist is. And then when we get to that point, then we can start calculating joint angles for joints 1, 2, and 3. So now we're back on the spreadsheet looking at the inverse kinematic side, and we need to work our way back from the end of the tool back to the center of the spherical wrist. So what we know right now is we know the XYZ yaw, pitch, and roll of where the end of the tool pointer is. And so the first thing we want to do is take this and turn it into a transformation matrix. So looking here at this first one, starting right here, this is R06 plus T plus the tool. So we're going to take and build this rotation section first. And what this is basically just like we went over in the first half of the video where we learned how to create a rotation matrix from the yaw, pitch, and roll. We're using this exact same formula here, and I have a copy of it right here. This is the same formula from earlier. And so we're just going to plug all these numbers in, the yaw, pitch, and roll, into this formula and build this rotation. So this is going to give us, in matrix format, the rotation of where the end effector or the tool currently is. Then we simply copy in. You can see how it's just directly linked to the x, y, and z values. So we have the x, the y, and the z values, and then we have, like before, 0, 0, 0, and 1 to complete the this transformation matrix. So now we have a complete transformation matrix that gives us a definition for where the end of the pointer is. And now the next step is we want to work our way backwards from the tip of the pointer back to J6. So in the interest of keeping this linear and understandable, I've redefined the tool frame here. So this is exactly the same as what we looked at earlier on the forward kinematic side. This tool frame, it's exactly the same thing. I just thought it would be easier to follow if we had it in both places so that we could follow the math all the way down through. So this is simply just a tool frame, and if I put in a value up here on the input, it's going to affect and manipulate this frame or this transformation matrix the same as before. So if I was to put in 100 in the Z, you can see it puts in 100 in the Z, and so on. So this is just our tool frame, and now since we're working our way backwards from the tool frame, we need to be able to invert that tool frame. So we need to create an inverted version of that tool frame. So one thing to keep in mind when we're creating an inverse matrix, that when you multiply the original matrix times its inverse should equal the 0 zero rotation or the identity matrix, and that's what it already is because I don't have any values in here. But if I was to say give the z value some value, you can see, we'll get to this in a minute, but you can see the z value is negative 100 on this frame and it's positive 100 on this frame. So if we're to multiply this frame by this frame, the output should be the identity matrix or a zero rotation matrix. So that's just something to keep in mind when you're inverting a matrix. So there's a lot of software tools out there to handle creating an inverse matrix. To actually invert a matrix manually is very mind-numbing. It would take about an hour-long video to go through. There's a couple different methods for doing it. But given that this isn't just a standard 4x4 matrix, in linear algebra, this is actually a transformation matrix with a rotation portion and a displacement portion. There's actually a trick or a shortcut to be able to very quickly turn this into an inverted version of this matrix up here. So in that little shortcut, we're going to focus on the rotation portion of the matrix. And that's these portions here. And so if you recall, diagonally through the center, these three cells are all ones when there's no rotation. So if we want to reverse that portion, we can just transpose it. We can basically flip it. If you think of this line through here as an axis and flip it, and we'll take this cell and move it across to this corner. We'll take this cell, move it across to this corner, and then this cell and move it across to this side, as if the whole thing just flipped along this axis. And by the same token, this one comes to this side, this one comes to this side, and this one comes to this side. That is basically just transposing the rotation portion of it. So if we take a look at that, and we look at what we've done in these cells here, this one directly references the top left corner, this one the center, so these don't move. But if I look at this top right, if I look at this top right, it's just grabbing the cell from the bottom left. And if I look here at the bottom left, it's just grabbing the cell from the top right, and so on. So you can see how it's just grabbing the cell from the other side. So all we've done is taken this rotation portion and flipped it over about this axis. So that transposes or flips the rotation portion for us, but then we still have to deal with the XYZ portion in the displacement. Now these are still directly affected by the rotation, or where that tool pointer is pointed in space. That tool pointer, if we gave this a value of say 5 in the yaw, then it's going to change the rotation on us, and that's going to directly affect the position. So let's put in a z value while we're at it. Let's put 100 back in there. So it's going to directly affect where these values end up in space. So let me put a 5 in each section so you can kind of see this a little bit better. So now we've got a yaw, pitch, and roll applied to our tool. So now our tool pointer is not straight anymore. It's pointed at some funky angle at 5 degrees in each direction, and you can see how that directly affects the XYZ position displacement in space. So the point I'm trying to make is that these can't be directly transposed over. They still have to be multiplied by the rotation that's going on. So that's what we have here. If you look at this X value, this is basically going back to some linear algebra and multiplying matrices like we did before in the earlier part of the video, and it's multiplying the XYZ times the top row, and then the second one is the XYZ times the second row, and the Z is the XYZ times the bottom row. So it's still multiplying all three of these values by the rotation. It's just multiplying a single column matrix by a 3-column matrix and placing those values here. So now that we've done that, now that we've flipped our rotation and multiplied the X, Y, and Z times that rotation and placed it here, then we also need to negate it. It needs to be negated. So if you look at these formulas, there's a little minus sign up here at the beginning. And so all of these are negated. And so now that's a shortcut to creating an inverted frame. And this little shortcut only works for a transformation matrix where we have a rotation portion and a transformation portion. This would not work for a regular 4x4 matrix in linear algebra. So that is how we get to our inverted tool frame. And so the next thing we want to know is, okay, well, now that I've got my inverted frame of the tool, and I know where the tip of the tool is, how do I work my way back to the to the spherical wrist? So our next frame, so as we work our way down, this next frame, the R06, this is going to represent the tool flange on axis 6, and all this is this frame, our original end of the end effector, or end of our tool pointer, multiplied by that inverted frame, and that gets us back to where the joint 6 is. And so now this gets us to the tool flange on joint 6. And now we need to go back even farther. We need to go back from joint 6 back to the center of the spherical wrist. So that operation we just did got us from the tip back to the end of 6. But now we need to take from the end of 6 and get back to the center of the spherical wrist. So now we're going to take it all the way back to this portion right here. So the next thing I've done is I've created a frame called R06 negate, and all this does is this is just a zero rotation matrix, but in the Z portion I've grabbed the inverse of our offset for the D length from the end of our effector back to joint 5. So this D value, this D 36.25, if we go back and look at our model right here, this D6 value is the value that goes from the end of our end effector back to the center of the wrist there. So that's what we have right here, is that value negated. We've got a negative 36.25 on the Z portion of this, and then for our final transformation matrix, that is just the previous R06 frame. This is the frame we got after we went backwards from the tip of the tool back to the end of the joint 6 end effector, and then we multiply that times the negation of that length, that arm length, and that brings us back to, and that's what gets us to the center of the spherical wrist. So this frame now represents the center of the wrist. This XYZ, this is the position in space where that is. And so now we can start working on calculating our joint 1 angle. So that's the next thing we're going to do. So now to calculate the joint 1 angle, what the actual angle is, we're going to refer to this little diagram here for the next few steps for calculating joint 1, 2, and 3. For joint 1, you've got this top-down view, so we're going to use the atan function to get this angle here. So if I click into this cell, you're going to see a bunch of if-and statements. Doing if-then statements in Excel is a little bit messy. You have to do if-ands and then stack them up, and it gets a little bit crazy. But anyway, what this is doing is it's just the same formula. It's just looking at a couple different conditions. It's just taking the atan of the x divided by, the y divided by the x to get that angle. So if I look at a top-down view of my robot, and this is my 0 line going straight up, and then let's say that I've jogged my robot, some amount of degrees in this direction, and I run that function, the atan of y divided by x from this position in space, it's going to give me, this angle here, which is what I want. But if I, for example, jog the robot, past 90 degrees, then, the 0 line keeps going. It's going to give me this angle right here. It's going to give me the wrong angle. So what that series of if-then statements says is just if it's more than, if the coordinates are, beyond 90 degrees, then take 180 degrees and subtract this from it to give the correct angle for J1. So that's what those if-then statements are about there. So just to show that this works here, if we go back up and let's say we put in 5 degrees for our J1 value, that's going to equal out, this is our Cartesian coordinates, so let me copy those and then paste the values back over to this side, and you can see it's going to run through that whole calculation, figure out where the XYZ is of the spherical wrist, run that atan function to return the degrees of that position. So now we have 5 degrees, and then that just gets transposed up directly up to this, that's just looking directly at that cell right there. So now that we know the angle of J1, we can move on to calculating joints 2 and 3. So if we look at this diagram, the rest of these calculations are going to be done from a side view. We know the X position of this point out in space, and we know the Z position. We know the X, Y, and Z. So basically the ones that matter here is the X and the Z of where the spherical wrist is in space. Now I know what this offset value is, and I know the X position, so I can start figuring out all these link lengths and angles. L1, L2, L3, and L4, these are all lengths that we're going to figure out. Those lengths will help us then calculate out some angles using trigonometry, and then we can figure out where the joint 2 and joint 3 angles are at based on all of this. So something I wanted to point out here when we're looking at a side view of the robot, and we're going to be basically calculating out or figuring out a number of triangles to figure out, what this angle value is and what this angle value is. The problem is that if I were to, jog joint 1 away, now none of those angles are going to be correct anymore. So that's the point I want to make, is that the robot mathematically needs to be back at 0 for joint 1. So we're looking at a perfect profile of a side view to make these calculations. So since I've already figured out what J1 is, I already know what it is, I don't really care about J1 anymore. So now I want to kind of put J1 back to 0 for the remainder of these calculations. So mathematically, that's what we're going to do. We're going to force J1 back to 0 so that we can run the rest of these calcs here. And so the formula for that, I have that right here. What this is the new X value. If I put X back to where it was, the X value is going to be X times the cosine of theta minus Y times the sine of theta. So if I look in the cell, that's what we have here, is that same formula right here, where we're looking at the X and Y values of the spherical wrist and factoring in the joint angle to essentially move it back. So essentially from a top-down view, let's say that joint 1 is at some degrees here. So here's our center of our spherical wrist, and what we want is we want to put joint 1, at least for these calculations, we want to put joint 1 back to 0 so that we can basically be looking at a profile view when we run the rest of those trigonometric functions to get angles 2 and 3. So that formula that I just gave you on the spreadsheet, all that's going to do is take this point, and it's just going to put it back. It's going to rotate it around the axis and put it back to 0. It's basically, if this is on our spreadsheet, it was 5 degrees. This is more than 5, but it's going to take that 5 degrees, and then it's going to take the X and Y positions and move them back. Z doesn't matter. Z is going to stay the same, so our height's not going to change. So all we care about right now, more or less all we really care about, is the X, but that formula is going to move the X and Y and rotate them back to 0. So mathematically, we're just setting joint 1 back to 0 degrees so that we can run those calcs. So essentially right here, what we have is this is what the X would be if joint 1 was not at 5 degrees. If joint 1 was at 0, it would be 248.3, not 247.35. So to illustrate that, we can come over here and put joint 1 back to 0. That'll give us this. These are our Cartesian coordinates. We'll copy that. We're going to paste the values back in. and now joint 1 should be at 0. And you can see here now they agree. The calculation on the spherical wrist shows x at 248.3, which is what we had before when we used this equation right here to mathematically force it back to 0 degrees. So now we're going to go through this diagram and we're going to start calculating out these lengths to help us get some of the angles that we need. So the first one is L1. So you can see right here is where we're calculating L1. And all that is our current x position, which is how far over we are here, minus the shoulder offset A1. So what you see here is the x position minus A1 over here. So then let's jump forward and look at the L4 length, this length right here. The L4 length is simply just the z height of the spherical wrist. So if we look at that one, that's just going to be our z height minus the D1 shoulder offset. So right over here, the D1 shoulder offset. So that's how we get L4 to get this length right here. Then next, let's jump back up to L2 to see how to get that length. That's just the hypotenuse of a right triangle. So that is just going to be the square root of L1 squared plus L4 squared. And so then the last length that we need, or the last length that we need, is L3. And so L3 is basically the same thing again. It's the hypotenuse of a right triangle. So we've got the D4 and the A3 values there. So if we look at L3, that's just the square root of those two arm lengths right there. So that's how we get that length. Next, we want to go through and start getting all of our angles here. So we're looking at theta b, and this is basically, we can get that just by getting the atan of L1 divided by L4. That's just the base and the altitude of a right angle triangle. The next angle we want to get is theta c right here. So this is a non-right angle triangle, so getting the angles from a triangle that's not a right triangle gets a little bit more difficult. I've got this pasted in here, this set of formulas for finding angles. So if we look at theta c, that is basically this formula right here. Using that formula to figure out that angle right there. Then we have theta d, that's our next angle we want to figure out. So if we look at that one, theta d, that formula right there is just following this formula here to get that angle right there. And then next we have theta e, that's this angle right here. And again, that's just a right angle triangle. So that's just taking the atan of the base divided by the altitude of that triangle, which just ends up being the d length and the a offset of the arm lengths of our robot. So then after we get all of those figured out, then we can actually figure out what the angle is for J2. So if we look into this cell, we've got some if-then statements nested in there. And basically what's that saying is that if the spherical wrist is forward of J2, then J2's angle is going to be theta c plus theta b. Otherwise, if the spherical wrist falls back behind J2, then it's going to be the inverse of that. And then also if the spherical wrist is above J2, if it's up in the air where it's shown here, then it's going to be theta c plus theta b. Or if the wrist drops down below, if the robot is reaching far forward, then it's going to be theta c minus theta b. So that's how we get our joint 2 angle. And then lastly, we want to get our joint 3 angle. So if we look at that, and that is just basically is theta d plus theta e. Since some robots have an A3 offset or a shoulder offset from joint 3, that puts the D4 at a the actual arm length of the robot is raised above and not at the same angle as L3. So you have to add theta e to theta d to get the correct angle for the J3 arm, where that arm is actually at. So before we move on, I did want to point out that this is the most simple form of the geometric method of finding the joint angles for joints 1, 2, and 3. I would point out that this robot and this set of calculations on this spreadsheet do not have calculations for an elbow back configuration. And what I mean by that is if you look at joint 3, the AR4, that's as far back as just going vertical. If we look at some other robots, let's say we load an IRB-120, an ABB robot, and we look at that one also, I believe, has, wrong joint there, also has, doesn't really have an elbow back configuration. The robot just goes straight up. But let's load a different robot. Let's say, I think an IRB-140. That one should have an elbow back configuration. So what that means is it goes, vertical, but then it keeps going. So you have an elbow back configuration. So, when we did all of our calculations, we were doing triangles and doing calculations in this direction. If we had to start adding conditions to be able to go the other direction, there's a whole another subset of calculations we would have to do an elbow back. And that also brings into play a joint singularity, and I'll talk about that a little bit later when we get to the wrist. But in general, a singularity is when a joint has to cross over 0 when it can get to the same point from two different configurations. So, for example, turn off my pen here. If, let's say we had joint 2 is back and joint 3 is forward, then, I could reach this point in space right here. But with an elbow back configuration, I could also take and put joint 2 forward, and then with elbow back I could bring joint 3 back, and I can get to the same position in space but in a different arm configuration, which brings in some math issues because some of the mathematics becomes ambiguous, and then you have to have a configuration value assigned to it so that the controller knows which configuration you want the robot in. But we'll go over that a little bit later in a few minutes when we talk about the wrist singularities. Okay, so now that we've finished calculating joints 1, 2, and 3, now we're going to get into how to calculate joints 4, 5, and 6, which will be the wrist, rotations. That's going to give us our orientation in space with a spherical wrist. So now we want to figure out the angles for joints 4, 5, and 6. Now, keep in mind that now that we have figured out the joint angles for joints 1, 2, and 3, that is going to dictate where the spherical wrist is in space. So, for example, this frame up here, we now know where the frame is for joint 3. Keep in mind that even though joint 3, the frame is back here, that might not be as intuitive since joint 4 is, this entire arm rotates. And so essentially this arm, joint 5 and joint 6 all together represent the spherical wrist way out here. And technically the frame for joint 3 is way back here. But regardless, joint 1, you see how joint 1 is going to manipulate that frame for joint 3. Joint 2 is going to manipulate that frame. And joint 3 is going to manipulate that frame. So any one of those 3 joints dictates where this wrist gets reconnected to the robot. If you recall previously, we were in our minds, or mathematically, we are disconnected the wrist so that we can take joints 1, 2, and 3, figure out where that point in space is that the wrist goes back on. So if you think of it, that there's a frame here, that there's a frame out here on the end of it, and we have to take and reconnect the wrist to that frame so that we know where the wrist is in space. That's what we have to do next. So to figure out where that frame is in space for the end of joint 3, where we're going to reconnect the wrist, we need to kind of do what we did on the forward kinematics and create transformation matrices for joints 1, 2, and 3 so that we can multiply them through to figure out exactly in space where joint 3 ends and where the wrist connects to it so we can figure out those angles. Now, what I've done here is I've created a transformation matrix for joint 1, joint 2, and joint 3. And since we have solved, for what joints 1, 2, and 3 are, I can take these values and apply those to the DH parameters and basically do the exact same thing we did on the forward kinematics for joints 1, 2, and 3. So if we go over and look at the forward kinematics for joints 1, 2, and 3, and then multiplying frames, for joint 1 times joint 2, and then the product of that times joint 3 to come up with R03. That is exactly the same thing that we're doing over here on this side, only I'm not getting joints 1, 2, and 3's values from the input. I'm getting joints 1, 2, and 3's value from our calculation that we just did. So that's what we have here. This is just the DH parameters using these inputs to put together the transformation matrix C for joint 1, 2, and 3. This one here is joints 1 times joints 2, and then this one here is the product of that times joint 3. So now I have a frame that represents where this joint 3 frame is out in space. So now I have a target. I know where I'm going to reattach the wrist at. So now the problem is that I have a frame out in space with a rotation for joint 3. So if joints 1, 2, and 3 are all jogged to some angle, this frame is going to be at some rotation. And then I also have my overall rotation, so this shows the overall rotation, which basically includes this. So I have to stack these together somehow. I have to merge the overall rotation, which is basically this rotation frame here, and I have to stack it with this frame here. So what I need to do is I need to set this back to 0. Basically, I need to be able to figure out what its inverse is. So basically what we're going to do, like we did in the example before for the tool frame, is we're going to just transpose it. If I take and draw a line all the way through the corner of this frame, and then I flip it, that's all I'm going to do. Is I'm just going to take the rotation here and I'm going to flip it into this rotation frame. This is R03 transpose. So you can see here I've taken the negative, in this case negative 0.358, and I've moved it up to the top corner here, and then I've taken the positive 0.358, moved it to the bottom corner, and we've basically flipped this frame to come up with a transposed frame to invert the the frame of where we're going to reconnect the wrist essentially back onto the robot. And so then what we have here, our final output, this is everything we need right here to get the rotation of the wrist. This essentially is R03 transposed. That's the end of joint 3 where we're going to reconnect the wrist, and then we've got the the overall rotation. And this is based on the inputs of the yaw, pitch, and roll plugged in here. So if we multiply those two together, this R36 gives us the actual rotation of the spherical wrist, so that we can then extract what the actual joint values are of joints 4, 5, and 6 from this frame right here. So now extracting the joint angle values out of this R36 spherical wrist frame. This is similar but a little bit different. Earlier, if you remember, we were able to extract the Euler angles from a rotation frame. The formula is a little bit different for actually extracting the joint angles for joints 4, 5, and 6. And I have that formula up here to look at. Now, here's the part where I wanted to get into talking about singularity. The problem here on the wrist is that it can reach the same point from two different directions. So if we look at our robot right here, and let's say that we want to reach this point in space, and we've got some angle here for joints, for joint 5, that angle right there, we can reach the same spot by changing, if we jog joint 3 down to the exact same angle, and then jog joint 5 up to the exact same angle. Now we can reach the exact same point in space, but we've got the exact reverse angle for joint 5. So that creates a singularity. When joints 4 and 6, when it's passing through this point, when it's, if the robot was, trying to pass through this point, and let's just imagine that joint 4 and joint 6 become perfectly in alignment, that creates a singularity where the math is infinite. It can't solve for where, what the rotation is from joint 4 to joint 6 when they're perfectly in a line. So that creates a singularity, and the math is also ambiguous. This rotation frame cannot tell you whether joint 5 is up or down. It can't. It's a mathematical problem there. So that's why you see here on this little diagram it says, theta 5, and then it has a plus or minus, meaning that if joint 5 is positive, you use these two calculations to get joints 4 and joint 6's value, or if it's negative, you use this formula to get joints 4 or joint 6's value. So this brings into play a robot configuration, and what a robot configuration is a value that when you actually teach the position, you also stack on a little number or a value that tells you which direction your singularities are going in. So to illustrate that, I've got the AR4 software open, and I've got the robot with all the axes at 0 except for J5, which is tipped in the negative direction. So if I teach a position, it will teach the position with the yaw, pitch, and roll, but it adds a configuration, an end configuration, to the end of the move. And then if I jog joint 5 to the positive side and teach a position, it now adds an F to the end for the flip configuration. So that's an example of the configuration that's added to the end of the move to signify the wrist's configuration for that move. Now, most robots, when you're jogging and you try to jog through singularity, once axis 4 and 6 come into straight alignment, it'll throw a singularity error, and then you'll need to jog joint 5 just to get on the other side of singularity to continue moving up. Now, this simulation software, I think they're using Marlin code, Marlin open source kinematic code, which I think is a little bit more advanced, has some methods to get past through singularity, as does some of the more expensive robots. But I just wanted to point that out on what singularity is and what robot configurations are. Now, most robots have more than one configuration. The AR4 does not have an elbow back configuration, so I didn't have to worry about adding a configuration for the elbow. And joint 1 doesn't go beyond 360 degrees. The robot just goes all the way around like that. But robots that can keep spinning on joint 1 will also have a singularity or a configuration for joint 1. So a lot of times there's 3 configurations on a robot, whereas the AR4 only has 1 configuration. I didn't really see a need to do an elbow back. It just creates issues with a wiring harness. And the only time I've ever had to really utilize an elbow back configuration is when I've had inverted robots, for example, doing water blast applications and things like that. So to show an example of robots that have additional configurations, this is the FANUC manual, and you can see here they've got the flip and no flip for the wrist, being able to get to the same point from 2 orientations or 2 configurations. They've got the for the elbow configuration, there's the up versus the down, and then for when J1 is flipped around and J4 is flipped over, they've got the front or back configuration. So a lot of times if you're programming a FANUC, you'll see the FUT or NUT configuration values associated with each move. So the F is the flip or non-flip, and it's typically up. So it's typically up and it's typically front. So you'll typically see an FUT configuration, or if it's non-flip, you'll see an NUT configuration on that robot. And then on ABB robots, for example, you'll have CFX values for their configs. They have like CFX 0, 1, 2, 3, 4, 5, given different combinations. They put their configurations in different combinations of joint configurations for their configs. So that's just an example of where you'll see robots that can reach the same spot through these singularities and different configurations. So now going back to our spreadsheet, I have this wrist config cell here, and what this basically does is it just looks at the actual joint value to see what J5 is, if it's positive or negative. So in a real robot controller, when you teach a position, it's going to be able to know what the current joint angle is. It can look at the encoder, motor encoder, or resolver, and know which RISC config to apply when the position is taught. And then when it uses the kinematics to try and get back to that position, just given the given the Cartesian coordinates, it needs this configuration to know which side of the singularity to put the joint on. So going back to our calculation up here for joint 5, it's basically just following the center equation here, and it looks at the configuration and has a series of if-then statements. So if the configuration is positive, it'll take R33 and it'll be plus the square root of 1 minus R33. And then if the configuration is on the other side, then it'll take R33 minus the square root of this formula here and come up with calculate the J5 angle. And then the J4 and the J6 calculations, those will basically follow this formula up here, that if J5 is positive, then J4 equals A tan 2 of R13 and R23, and J6 will be A tan 2 of negative R31, R32, and then it's just the signs are reversed. If J5 is a negative value, then it'll use these calculations here, be a negative R13, negative R23, and then joint 6 will be A tan 2 of R31, negative R32. So if we take a look at that, it's basically looking at our spherical wrist orientation and grabbing the A tan 2 of those two cells, and J6 is using the A tan 2 with those two cells there, and the J5 is calculated off of the cell there. So that's pretty much it on how joints 4, 5, and 6 are calculated using this formula here. And I hope this helps people to at least get kind of a basic understanding of how the robot kinematics are calculated, both for the forward and the inverse. So let me know if you have any questions or if you spot any mistakes, and thanks for watching.